Which professional or amateur cyclist has not fallen yet? Those who did know that their collarbone is usually broken. And then an X-ray will be taken. So we learn that X-rays are used for searching bone fractures, but can also be used for analyzing any other matter. Apparently, those X-rays penetrate matter, and once detected, we can take a picture. But what makes X-rays so special? For that we must look at the part of the electromagnetic spectrum where these X-rays are. The frequency of these X-rays ranges from 10 to the 16th to 10 to the 19th Hz, way higher than those of visible light. Due to this high frequency, X-rays are able to penetrate matter. As said, X-rays are used for analyzing bone fractures or other irregularities in living matter. Here we are merely interested in how we can use X-rays for studying the structure of matter for battery research. In that respect, several techniques based on X-rays have been developed, such as single crystal diffraction, back reflection Laue diffraction, grazing incidence angle diffraction, X-ray reflectimetry, small angle X-ray scattering, X-ray powder diffraction, Rietveld refinement, and pair distribution function. However, we will focus solely on X-ray diffraction. When X-rays strike matter, they can be deflected, reflected, and diffracted. This last phenomenon is particularly interesting to analyze structure of solid matter on an atomic scale. That means where atoms or ions are present. Once a solid has a crystalline structure, the atoms have a nice long-range periodic arrangement, resulting in planes of constant distance. This can be seen in this transmission electron microscopy picture of a crystalline silicon particle. These planes will scatter the incoming X-rays according to Bragg's law, n times lambda equals d times the sine of theta, with n an integer, lambda the wavelength of the X-rays, d the spacing between the planes, and theta the scattering angle. Note that d is defined here for only one specific distance, but atoms arranged in various planes. Therefore, distances d are indicated by d, h, k, l, where h, k and l stands for the direction of the planes. Hence a specific XRD spectrum of crystalline silicon can be seen here. In essence, you can calculate the distance between the planes by measuring the distance between those in this transmission electron microscopy picture, and these should be in line with the results of the calculations via the Bragg relation. So it is important to understand how we can record these X-ray diffractograms. The X-ray diffractometer uses an X-ray beam that enters the sample house. Once striking the sample, the X-rays are scattered. This scattered beam is then detected in an angle of 2 theta. Since each set of planes in the crystalline sample has their own spacing, reflected by the HKL values, this then will result in a spectrum of constructive interference as specific to theta values. Therefore, you usually see a spectrum of intensities of the interferences at the function of 2 theta, depending on the HKL values. To generate X-rays, a metal is being bombarded with electrons, where several interactions may occur, leading to emission of various electromagnetic radiation, including X-rays. The wavelength of these X-rays is specific for the metal used, but it needs to have a relatively high melting point to avoid melting or sublimation under electron bombardment. Most metals give X-rays coming from emissions from the so-called K or L levels. These X-rays beams are usually paired in what we typically see as K alpha 1 and K alpha 2, with specific ratios in intensities. Depending on the software used to analyze the spectrum, the K alpha 2 intensities can be removed. The most used X-ray tube as the source for X-ray beam today is copper, but other tubes are used for specific applications. The spectrum that has been recorded can be used to analyze various properties of the material, such as for powders, crystalline structure of the material, cell dimensions, grain size of the material, and purity and concentration of the components as fitted via Rietveld refinement. Note that the particle is different from a grain, as shown here. A particle may contain more grains, where a grain is similar to a domain or crystallite. Nevertheless, a particle can also have only one grain or domain, as shown here for the silicon particle. Coming back to powder diffraction, a perfect crystal with sizes about say 1 millimeter will give us only a line at the constructive to theta angle. But this is never the case. Even for huge bulk silicon crystals we see a certain width, which can come from the machine, but also from the material itself. Nevertheless, if we crush the silicon to smaller particles, even to nanopowders, we see a huge increase in the peak width. This can be quantified by the Scherrer equation to calculate the grain or crystallite size, hence the diffracting domain. If a domain becomes very small, so no long order is being established, or when the solid becomes amorphous, constructive scattering will no longer take place, and very broad peaks are obtained. In the case of the silicon particle, where at the surface a layer can be seen by scanning electron microscopy, we can figure out that this layer is amorphous, giving the peaks underneath the diffraction peaks of silicon. Actually, it was found that this layer was typically silicon dioxide. X-ray diffraction can also be used operando, meaning measuring during charging and discharging. Here we take a lithium iron phosphate and silicon as the example. During charging and discharging of lithium iron phosphate, spectra were recorded at certain time intervals at specific interference peak at the 020, 301 and 311 peaks. Obviously, we can see the reversibility of the lithium iron phosphate during consecutive charging and discharging. Similarly, the silicon electrode was analyzed during lithium uptake and donation. Also here, changes of the crystal structure can be seen, as well as its reversibility or irreversibility. Note that the lithium iron phosphate and silicon X-ray spectrum are recorded with a silver and molybdenum X-ray source, respectively. X-ray diffraction is a strong tool to analyze materials and their changes during operation of a battery. That means batteries may be active during X-ray measurement, in contrast to you, where you must sit still.